Okay, just to reorient you to where we left off, we're still talking about data preparation, and we're still talking in the context of data splitting. We just talked about partitioning a data set, an original data set, into a training and a testing set. So now I just want to mention validation data. These are instances that are used to provide an unbiased evaluation of a model fit on training data when tuning hyperparameters of an algorithm. So let's say this is your original data set, and like we just saw, we broke it down into a training and a testing split. This is what we train our model on. We can further break down this training set into a training and validation set. And then what we can do is we can try training our machine learning model using different hyperparameters, different settings, right? And we can evaluate how well those settings perform on this holdout validation set, right? And even after we've optimized our hyperparameters, when we go to do our final model evaluation, we still have data held out that we can do our final model evaluation with. Now, notably, I do want to note that the terms validation and testing data are really frequently interchanged in the literature. It gets really confusing. So instead of focusing on what term they use, focus on, are they holding out data for purposes of a hyperparameter sweep? Are they holding out for purposes of a final unbiased evaluation? Pay attention to that more than anything. And question it. I've seen papers where they reported training accuracy results unintentionally. And that is like the worst sin in machine learning. Okay. When we use this validation set, if we're just doing one holdout validation set, and we're using it repeatedly, eventually that holdout knowledge is gonna seep its way into the model, right? So it will become more and more biased the more evaluations you conduct. All right. Sample bias. This is a good time to bring up this problem. You're probably already familiar with this concept, but modeling can be biased by training on data that's not truly representative of the larger population. I think we all already know this. And of course, this is going to result in a poorly generalizable model, which is the whole point. That's our whole goal. And there are really two scenarios to consider here in terms of sample bias. The first is during data collection. We can have sampling errors due to random chance or selection bias. However, we also need to worry about sample bias when we're doing data splitting, right? The partition you create might make a training set and a testing set that don't equally represent the larger population. You might have held out a test set that's super easy to make accurate predictions on, but a training set that have instances that are harder, right? Naturally on the data set, there are gonna be some instances that are really easy to predict and some that are hard. And so just by random chance, you could do a single partition that creates sample bias and gives you an inflated sense of how good your model is, or it might look like your model did terribly when in fact there was something there to discover. That's why we use k-fold cross-validation. This is one answer to this problem. This is a resampling procedure used to evaluate machine learning models on a limited data sample. We do this to address the risk of sample bias and data splitting. How do we do it? Well, we start with our original data set, and we shuffle the data randomly. I mean shuffle the rows. You're not damaging the data anyway. You're not destroying signal between outcome and features. You're just shuffling the instances. Then we split our original data set, and we'll just focus on up here, into k partitions. Here we have a k of 5. So and we do this, so if we have 5-fold partitioning, we break into 5 parts, and each time a different one of these parts is gonna be our holdout test set. And the rest, so that's our holdout test set, and the rest is gonna be our training set in each run. And what we're gonna do is we're gonna fit a model. Let's say we're just using decision tree as our algorithm. We're gonna fit a decision tree model in each of these situations. So we're actually gonna end up with 5 models. Now, this in itself isn't always desirable. You know, often we just want one model. We just want one model that we can apply and use. So there are ways around this. But in terms of getting an initial look at your data and understanding, you know, the relationship between variables and outcome, this is really the most rigorous way to start to go about it. You can always hone it down to a single model that you're gonna put into practice, or you can have all of these work together as an ensemble predictor. and I'll talk about that later. But for now, just understand that this is a really, I would argue, critical part of doing rigorous machine learning analysis. And then once you've trained all your models, you can look at their average performance on the problem to get a sense of how well that algorithm did on the data set. Okay, we just had a break, so skip over that. All right, next up, feature processing. We're going to focus on this green shape here and everything inside of it. So feature processing is all about improving the data representation so that machine learning modeling can achieve higher performance. This includes feature engineering, where we use our domain expertise to build new features from existing ones. So this is usually done by a human being. Feature learning. This is the automated version of feature engineering, where we're actually using machine learning or other strategies to automatically build new features from existing ones that we can then pass on to modeling. Then there's feature transformation. This is where we might want to scale the distribution. We might change the scale or distribution of features in the data set. And there's a few reasons for doing that. Dimensionality reduction, where we can create compact projections of features, and feature selection, where we want to remove irrelevant and highly correlated features. I'm going to go into a little bit more depth on all of these. Feature engineering. This is where we use domain knowledge, our own human expertise, to build new features from existing one. This technically differs from feature extraction, which we learned about earlier, right? If you have like video or images and you're extracting features from it. And it differs in that here with feature engineering, we're creating new features from ones in the raw data that we could have used directly for machine learning, right? It was already in a format that technically we could have just run machine learning on it. It can be conducted before data splitting because we're using our domain knowledge, not the data, to derive new features. Notably, feature engineering is a term that's sometimes very generally used to refer to all the parts of feature processing, maybe except feature selection, as well as feature extraction and formatting. Sometimes in papers, people say feature engineering, and they kind of mean all these things at once. I'm defining it more specifically here as what we just talked about. Process. How do you go about it? Usually you'd start by just brainstorming, right? Thinking about what might be useful features. Use your own intuition. Know that at the end of the day, in many ways, machine learning is it's kind of just a big dumb animal. It's a powerful but fairly dumb algorithm, right? You do want to help it as much as you can in terms of using your own human intuition to help build features that it's going to be able to really learn on. You need to decide what features you want to create, and you can usually test them initially. Like add them to the data set, do some exploratory analysis. Does the new feature you created actually have a stronger association with outcome? You can play around with it, or you can just engineer features and hand it all to machine learning and see if machine learning finds them useful. And this process, as is the entire cycle of data analysis and machine learning, can be cyclical, right? You can run a whole analysis and it can feed into another one. The main thing you want to be careful of in doing that is that you're not accidentally biasing, you're not doing that data leakage each cycle, adding in information that shouldn't be there when you evaluate your models. And you also want to make sure that you don't end up just having a multiple testing issue, right? Which is, obviously we worry about that in statistics, but in machine learning, if you run the same analysis again and again and again and again with the same random seeds, eventually you're probably going to find something more interesting than you did in an earlier run. So keep that in mind. Feature learning, the automated brother of feature engineering. So we're automatically using data to build new features from existing ones to, again, facilitate and improve modeling. This is also referred to as feature construction. And we can use machine learning strategies that basically test and evaluate combinations of 2 or more features from your original data set. It's basically looking for interesting ways to combine existing features. Not super unlike what dimensionality reduction is doing, except this is looking for feature combinations that are directly informative of our outcome, rather than just looking for things that capture variance in our data set. So here are a few examples, and I am giving biased examples because these are feature learning strategies developed by Dr. Moore's lab and some other people associated with his lab. First is multi-factor dimensionality reduction, or MDR. This was developed by Marilyn Ritchie and Dr. Moore and others. And the basic idea here is that you are taking the original feature space and you're creating n-way combinations of variables to explicitly look for epistatic interactions. And so you're taking multiple variables, collapsing them down into a single new variable that any simple machine learning algorithm can detect. So in other words, you can use a simple linear regression potentially to detect a complex interaction if you first use feature learning to make a more accessible feature, something that's easier for machine learning to learn on. Some other examples include algorithms called few and feet, developed by Dr. LaCava. And here it's using something called genetic programming to look for interesting ways to combine variables, again, to improve how informative they are when you get to machine learning. And then something my lab designed is called RARE. And this is for rare variant analysis. It tries to automate binning multiple features, right? How do you take features that have various states, put them together into a new feature that hopefully is more informative? So the theme across all of these is just improving the representation of features, that you're combining more than one together, so you can hopefully get more information when you feed it into a modeling algorithm. Feature transformation. This is to change the scale or distribution of features using some kind of mathematical transformation. It's going to transform the relationship between the independent features in your data set and the dependent variable. Usually you do this on a variable by variable basis, or you can do it across all variables at once. There is some overlap with feature engineering here, because you might have prior knowledge that it's really important to use a certain transformation, maybe a log transformation of a variable, to put it into a linear relationship, right? So you can also think of feature transformation as part of feature engineering. But you can do it with or without domain knowledge. So in changing the distribution, right, I mean that you're transforming a feature's values into some new probability distribution. And here are some examples of different probability distributions that a variable can take. And this can help to linearize feature association with outcome, as I just mentioned. Then there's scaling, right? And this is where you transform feature values so they fit within a specific scale. For instance, 0 to 1 or 0 to 100, or something like that. This may seem trivial, but interestingly enough, a number of machine learning algorithms rely on features having the same scale, deep learning being one of them. Also, regression, linear and logistic regression, they can perform without scaling, but you can interpret feature importances from the coefficients more reliably if you've conducted scaling first. So you can scale your data always before machine learning. It won't hurt all machine learners, but some machine learners really benefit from it. So it can't hurt to include scaling as part of the standard pre-processing of your data. Dimensionality reduction. So here we're creating compact projections of the features in data. So this can be useful, and it's often used when you have data sets with tons of features. So genomic analyses where you have hundreds of thousands or millions of variables to consider. You're basically transforming data from a high dimensional space to a low one with the goal of reducing the number of features you're going to hand to modeling. It attempts to address the curse of dimensionality. And this, without going into any details of these methods, this is just a tree representing different types of dimensionality reduction methods. So these are decomposition methods, manifold learning, and model-based approaches. These methods can either be linear or nonlinear. The nonlinear ones have a star, so all of manifold learning are nonlinear. I'm not going to go into more details here, because Sorry,
what's dimensionality of data?
What I mean by that is how many features, how many instances. Mostly how many features. So if you have 100,000 features, that is a high dimensional feature space, is what I like to say. And so you want to reduce the dimensionality down. It also has to do, so the curse of dimensionality is when you have a high dimensional space and you're looking for combinations of variables, it's rare, across the whole data set, you're not going to have too many people that have a specific combination of 2 or more variables. So there are fewer samples to support detecting more and more complex interactions between variables. Okay. We're not going to go into detail here, but I wanted to create this slide as a reference. Here are a bunch of unsupervised machine learning algorithms. Not complete, but a pretty exhaustive list of well-known unsupervised machine learning algorithms. And you can use these algorithms for many different purposes, some better at some things than other, but you can use these for exploratory analysis, to facilitate data cleaning, feature extraction, or dimensionality reduction that we just covered. So you can see there are some general families of methods, and I encourage you to explore this more. It is, going into detail here is unfortunately beyond the scope of this session. All right, lastly in feature processing, we have feature selection. So the goal here is to remove irrelevant or highly correlated features in order to reduce our feature space, the dimensionality of our data set. So down here we can see here's all features, and then a subset of those are relevant. That means they have some kind of relationship with the outcome we're trying to predict. And then even within that, you can have features that are relevant and non-redundant, right? Because you can have some features that are highly or perfectly correlated with one another. And typically, the goal of feature selection is to remove both non-informative and highly correlated variables, but it could just be focused on removing uninformative features. We might just keep all of the correlated variables in there. So you can apply this to, you can apply feature selection to all of the original features in your data set, as well as those you've introduced during the other parts of feature selection. So if you used feature engineering or feature learning and you've added those new variables to your data set, feature selection is a good point where you might filter them out because they turned out not to be terribly useful. So why do we do feature selection? Well, overall, it reduces the computational burden, right? When we get to modeling, as I said before, the fewer the number of features in your data set, the easier it is for the models to perform well. Also, it's just reducing the overall noise in your data set. By removing non-relevant features, it's going to slow down your ability to find the important associations. And we can do feature selection, generally speaking, I'm just going to talk at a high level, either manually, using our own expert knowledge. Like maybe we know that we just want to include features within a certain biological process or a pathway, right? We have no reason to believe others are important for some reason. Or maybe we know that the disease has no genetic basis, and so we just exclude those variables, right? So we can use our own knowledge to conduct feature selection. Or you can use statistical tests of association or machine learning algorithms entirely focused on determining what features to keep and which ones to get rid of before modeling. A little bit more on removing redundant features. So correlation is a bivariate analysis measuring the strength of association between two variables and the direction of a relationship. So we can look at correlation with a number of correlation metrics, like Pearson, Kendall, Spearman. And data cleaning should have probably already addressed removing features that are 100% correlated, right? Because it's just redundant information. Although you do want to keep a record of which features were correlated, because if you're trying to track down causal factors, right, and you find a strong association, you're going to want to know what that strong association was correlated with that you removed from the data set, right? You can also remove highly correlated features. For example, this is an arbitrary threshold, but those with a correlation higher than 90%. However, notably, critical information in your data can technically still be lost even when removing one of a pair of features that is highly correlated with the other. So imagine here's two classes here, and you can see that these variables are highly correlated with one another, right? The x and y axes gives us an overall data pattern that has a high correlation between those variables. And yet, if we were to have removed one of these variables, we would have lost the ability to discriminate between one class and the other. So just a word of warning, I don't know how often this happens in real world. Mostly when we develop methods, we think about theoretical extremes of what is mathematically possible, and then we work backwards from there, because we don't know what real biology is going to present us. Feature selection, supervised method families. So in conducting feature selection, there's three general approaches to doing this. The first are to use filter methods. And basically this is done before machine learning. And we're using a simple proxy measure to rank our features and then remove the lowest performing ones before we do modeling. This is fast, and it's nice because it independently gives you an estimate of feature importance, and I say it's independent of a specific machine learning algorithm. So you can use this as a precursor to do feature selection and then run a variety of machine learning algorithms. They're all kind of treated the same way in terms of what features are passed on. Some examples include mutual information or some kind of feature outcome correlation. There are also wrapper methods, right? And so here you've linked the feature selection process with the modeling process. And so basically you're testing out potential subsets of features, creating a model and see how well those subsets do. This is computationally expensive, it doesn't scale very well, and what it gives you are features that are specifically improving the performance of a given machine learning algorithm. So there could be a little bit of algorithm bias being put into the results. And then you have embedded methods, which integrate feature selection with modeling. It's really doing both things at once. These are not as expensive as wrapper methods. They're less prone to overfitting, but they do, again, give you more algorithm-specific results, right? It's optimizing what features are selected for the algorithm, for the model that it's being trained. Some examples of this are things like L1 lasso regularization, and even a decision tree is selecting what features goes into it. Okay, so this is what we've covered in data preparation. We get to move on now to modeling, the fun stuff, and then we will end later with post-analysis. All right, machine learning modeling. Here's again our overall pipeline. Modeling is the process. This is actually one of the quicker sections. So modeling is the process of training a machine learning model with some kind of ML training algorithm. The model itself is an artifact created by an algorithm during the training process. Modeling can and should include what algorithm do I pick? Which one do I select? Which set of algorithms do I select to run? How do I optimize the settings of each algorithm to give them all the best chance of performing well? How do I then, once I've picked my hyperparameters, train a final model and move on from there? How do I evaluate my models based on whether I'm doing classification or regression? And lastly, towards interpretability of our models, how do we conduct feature importance estimation? I like this quote from George Box. All models are wrong, but some models are useful. Remember that a model, of course, is a simplification of reality. Simplifications are going to be based on assumptions, and therefore there's some kind of bias being integrated into the modeling. Also, assumptions are going to fail in certain situations, and a model will therefore never represent an exact real behavior of a system you're trying to capture, right? I think most of us can accept that. However, a close enough model can, of course, be useful to describe the behavior in practice. Each algorithm in the model it generates makes unique assumptions and has a uniquely biased perspective of the world it's trying to encapsulate in the model. And therefore, offhand, I'm going to argue that more often than not, it's useful to look at the perspectives of multiple machine learners. The no free lunch theorem, NFL. This states, in terms of optimization as a problem in general, not even necessarily machine learning modeling, but in terms of optimization, any two optimization algorithms are equivalent when their performance is averaged across all possible problems, all possible data sets you could ever analyze. What this suggests is that no single algorithm can perform optimally on all problems. There is no one ring to rule them all. This doesn't mean that algorithm choice doesn't matter. It does mean you shouldn't always use the same, your favorite algorithm. I know it's tempting for every problem, because chances are you go from one data set to the next, all of a sudden your algorithm does really cruddy compared to something else. This also applies to hyperparameter settings for a given algorithm. Don't always use the same settings. If something worked well for one problem, that doesn't mean it's going to work for another one, even if it has the same number of instances and features. Don't always use the same default or default settings for hyperparameters. Okay, how do we deal with the no free lunch? For any algorithm, you want to first test and optimize hyperparameter settings. That's a given. Then we have some options. You can try to choose the most appropriate single algorithm to run. Maybe you don't have computing resources handy. You're limited logistically, and that's fine. That happens. So you can try and pick the best algorithm, and choosing the best algorithm depends on a lot of factors. What's the data type you're tackling? What computational resources do you have access to? What assumptions are you willing to accept in analyzing this problem, right? Linear regression is super fast and easy and often performs well, but are you willing to assume that there are the problem is totally linear, that there are no nonlinearities in the data that you want to capture? This approach, of course, is the quickest and easiest, but it's also the riskiest. Number two, apply, compare, and pick the best performing of multiple algorithms. Let's run, so pick algorithms with different strengths and weaknesses to get a diversity of perspectives on modeling. I'd suggest 3 or more algorithms, or as many as you have time or the resources to apply. Number 3, you can utilize wisdom of the crowd with ensemble algorithms. I mentioned this earlier, or meta-algorithms. Basically here, you're combining multiple trained models and looking at their combined votes or their combined predictions and integrating them. The idea being that, on average, the votes of many experts are going to give you better results than relying on the same expert all the time. However, when you do this, now your predictions are the least interpretable of all of these, right? Because to understand how the prediction was made, you need to understand the contribution of all the people contributing to the decision. All right, let's get back. You saw this slide earlier, and I mentioned that there are all sorts of machine learning families out there. And I'm going to use this as a segue to give you a list of specific machine learning algorithms. You might recognize some or many of these names, or none of them if you've never touched machine learning before. I'm not going to go into detail here, but again, this is for reference. I've tried to group commonly known used machine learning algorithms into respective groups, and there's some groups that are related to one another, like regression is related here to regularized regression. Decision trees have a connection to ensemble tree-based learning. Instance-based methods have a connection to support vector machines, and neural networks have a connection to deep learning. These are all supervised machine learning algorithms, or they're machine learning algorithms that can be used for supervised learning. Some of them can be used for other kinds of learning, but at the very least, you can use them for supervised learning. I've highlighted some in red now. If you're looking for a starting point, you want to run 1 or 2 or 3 algorithms, these are my recommendations as starting points. These are these aren't the only ones you should ever use. There's no guarantee these are going to give you the best results. But if you're looking to get started, this is a pretty good starting point. A lot of these are pretty easy to run. They're relatively fast, some of them, not all of them. They're very well known, widely used. Anyway, these are possible starting points. At this point, let me take a moment to differentiate 2 ways to define regression. It kind of has 2 meanings depending on the field you're coming from. In statistics, regression just means you have a modeling method that's attempting to determine the strength and character or relationship between one dependent variable and a series of other variables. Straightforward. So linear regression, logistic regression, you're fitting a line, right? In machine learning, when we hear regression, we're almost always talking about predicting a continuous valued outcome, a quantitative outcome, which is confusing because we have linear regression and logistic regression. One's doing classification, one's doing quantitative prediction. But then you go to machine learning, and whenever you hear regression, we're almost always talking about a continuous value prediction versus classification. All right, more on algorithm selection. First off, pick an algorithm or implementation that is applicable. Not all algorithms are going to be. So first off, Are they suited to the learning type you're doing? Do you have labeled data so you can do supervised learning, or do you have partially labeled data, unlabeled data? What are your options algorithmically based on the data you have? What is your outcome type? Not all algorithms can or are particularly good for either classification or regression. Some are much well suited to one rather than the other. Some you can technically do both, but it's just not as good at handling one. Or feature types. Not all algorithms can handle mixed feature types. This is why early on I focused on numerical, categorical variables. By default, most implementations of machine learners can only handle variables as numeric values. They need to be specially implemented to properly treat categorical variables as they should be categorically, and numerical as they should be numerically. So be aware that you might need to do something called one-hot encoding. I'm not going to go down that rabbit hole too much, but if you have categorical variables and you want to ensure that your categorical variables are being treated as such, you need to take that variable and do something called one-hot encoding. General advice, start simple. If there's a strong, simple relationship among variables associated with outcome, almost any method is going to find it. It doesn't matter which one you pick. So you might as well pick something fast that makes simple assumptions and is easy to use. So for example, I recommend starting with linear logistic regression, decision trees, and naive Bayes. Super easy. If the problem has a simple relationship, they're probably going to do pretty well, or at least one of them well. To illustrate why it's not always important to use a sophisticated method, and I'm not saying you shouldn't use sophisticated methods. I'm all about developing new sophisticated machine learning methods, but there's a time and a place for everything. So let's say we have two examples. We have a simple model made with linear regression, and then a really complex model that we made with random forest, let's say. And we get a much better training accuracy with our advanced model, right? We're basically, you can tell already this is overfitting. And then when we have some new variables added, our testing data, our simple model can do much better than our complex model. Now, this is not a rule. Certainly, you can do better with a more sophisticated algorithm, but it's not always going to be the case. When picking an algorithm beyond something simple, these are the things you need to consider. And I'm going to talk about a few of these, but not all of them today. Consider the strengths and weaknesses of different algorithms. What assumptions do they each make? What are the computational requirements to run them? Like, are they going to take a week to run, or an hour, or a minute? Data size. Not all algorithms can handle big data well. Like k-nearest neighbor classifiers go super slowly when you have a lot of instances in your data. Like I just ran some analysis with 5,000 instances, and it's been a week, and it's still running. Interpretability. Is it important to you that you can understand how your model makes predictions? In some domains, to some people, all they care about, and rightfully so potentially, is making an accurate prediction. But for many of us, I think in medicine, this is a great example of where it's really important. We need to understand how the predictions are being made in order to have faith in the predictions, in order to actually be clinically useful. So what do I mean by interpretability? Humans can readily understand the reasoning behind predictions or decisions made by the model. So why do we care? Again, when accurate predictions alone is insufficient. We need more than just accurate predictions and some data sets to convince us that it works. This is to promote trust, to address potential legal accountability for decision making. Importantly, to identify bias. How do we know if our model is making biased decisions if we don't understand how the decisions are being made? And knowledge discovery. If, as a researcher, we care about understanding more about diseases or these problems. So we need interpretable models. And lastly, just it tends to pair with simplicity. Often, having a simpler model sometimes has logistical benefits. Some machine learning algorithms are actually really slow to apply in practice. You've already trained the model, but it actually takes a while to make a prediction. And that might not matter. Maybe it takes 5 seconds to make a prediction. But maybe that prediction is the difference between life and death, right? Depends on the context. This is a subjective, totally subjective assessment of the trade-off between accuracy and model interpretability. Please do not take this as a rule. This is a rough guide. But in general, this gives you a rough idea of what kinds of methods are more or less interpretable. Truly, probably the only truly interpretable machine learning algorithms, like truly interpretable, are decision trees, maybe linear regression based, or logistic regression based on how it's run. And genetic programming is something we won't get into today, but it also grows trees that you can directly interpret and understand how they work. And then there's also a field of methods that I study called rule-based methods, which also is very interpretable, but there's trade-offs in interpretability there. Okay, real quick, a little bit more on interpretability, black box model. How many of you have heard of a black box model? Raise your hands. Yeah. So these are models that are sufficiently complex that they're not straightforwardly interpretable by humans. We can't decipher clearly how or why the model makes predictions. Right, so this is a black box. Maybe we get a really accurate prediction, but in fact, we want to understand what is driving that prediction. Okay, moving on from algorithm selection. Now let's talk about hyperparameters and hyperparameter optimization. How are we on time? Okay. I'm going to eat into the break a little bit, just try and make a little bit more progress before we move to lunch. Is that okay? All right. So hyperparameters. A hyperparameter, as we learned before, is something that the user can tweak to try and optimize machine learning algorithm performance. So most algorithms have default settings you can use for these. And they're a good place to start if you're learning. Just try it out. Just use the defaults. But eventually, you're going to want to explore hyperparameter settings because they will impact performance going from one problem to the next. So default parameters are just a starting point. Don't rely on them. Here's an example with a decision tree. This is the one line of code I mentioned earlier. This is a Python code to train a decision tree classifier. You don't need to really understand that. I just want to illustrate how an algorithm, in this case a decision tree, can have a variety of hyperparameters that are really important and can impact how the algorithm works. And I'm not even going to go into detail of what these hyperparameters do at the moment. I just want to point out that there are things like, well, I'll mention max depth. Right? How deeply can the tree be trained is an example of a hyperparameter that can absolutely impact how good this tree is at the end of the day, how overfit it is, how generalizable it is. So how do we find the best configuration of hyperparameters for an algorithm? We do this with a hyperparameter sweep, where we search for the best hyperparameter configuration on a given data set. It is data set dependent. As you go from one data set to the next, one problem domain to the next, absolutely expect optimal hyperparameters to change. How do you go about this? You can either, if you're a machine learning expert, you can sit down and you can use your own intuition from past experience to try and make educated guesses. You could do a manual search. Doesn't always work. It's really hard to guess, even with experience, the best hyperparameter settings. Another option is to do a grid search. Imagine the x and y axis on this grid represent two hyperparameters we're trying to optimize. Let's say tree depth and the number of samples that end up in the decision tree leaf. Note that we might be optimizing more than just two hyperparameters at once. There might be 10 or 15 that we're trying to optimize at the same time. But for the purposes of illustrating this, we just have two. A grid search means that we're picking a predefined set of values. So tree depth might be a tree depth of 2, 5, and 10. And then the number of leaves might be 2, 10, and 20, right? And we're going to explore explicitly those combinations. But we're, in a way, limiting ourselves to just these points in the space. And we can see from the colors in the background, the red colors mean we had a stronger success in modeling, and blue means we got poorer performance. So it's a good way to explore the space in a structured, consistent way, but you might miss out completely on where the optimal parameters are. Another way to do this is a random search. Right? You're just randomly trying out combinations of values that are valid. And again, this has strengths and weaknesses, as you can imagine. It's not guaranteed to find the optimum, but gives you a little bit more flexibility than a grid search. But at the same time, you have to decide, well, how many random tries do I make? And that can influence performance. Then we have what I might characterize as smart searches, although don't expect these to absolutely always give you the better performance. They're not guaranteed to do that. Examples include a new package that I've become a fan of called Optuna. But there are other strategies to do this, including evolutionary optimization. But basically, you're trying to more intelligently explore the space by trying out values. And then if one trial gives you a particularly good value, explore more in that area. That's the basic idea. And then training. So now we've picked our best hyperparameters, and we've done so on our holdout validation set. But now we're going to go back to our full training chunk, and we're going to train our final model using our best parameters hyperparameters that we've picked. And this is pretty straightforward. So maybe during the hyperparameter optimization, this was the best performance we got in terms of accuracy of the model. And then we train our final model on the whole data set, and we get a training accuracy of this, and a testing accuracy and evaluation accuracy of, in this case, 0.757. Training accuracy says very little. You can generally ignore it. It does tell you if the algorithm's learning something on the data, but in terms of evaluating and presenting your results, generally just ignore training accuracies altogether. Okay, so I'm gonna stop there. We have 3 minutes before lunch, so I will take a couple quick questions if anyone has any right now. So you're asking, the characteristics of the population that you want to be homogeneous, right? So for instance, a covariate, right, like age. Yes, and in fact, a pipeline, one of the things we do in the automated pipeline that you can take home and play with is exactly that. We allow the user to specify matched groups, right? So age groups, for example. So you're gonna pick cases and controls that have similar ages. And then when you do the cross-validation partitioning, or any partitioning, what it's gonna do is it's an attempt to balance them. So you have similar covariate controls in the groups. That's one way that you can try and address covariates in a machine learning analysis, is to create those matched groups ahead of time and then make sure that you're preserving those matched groups within each partition so they're not separated. Absolutely, and I'm sorry, I didn't explain that clearly enough. The hyperparameter optimization is doing modeling. What it's doing is it's taking, so you have your training set for this partition, and it's breaking that up, as we mentioned earlier, into a sub-training and a validation set to evaluate our hyperparameter selection. And it will start with some initial hyperparameter to test, some combination of hyperparameters. And it'll do modeling on that sub-training set. And then it'll evaluate that attempt using the validation set. And it'll say, okay, is this the best one I've gotten so far? And it'll hold on to it if it is. It'll say, oh, this is my best configuration that I found up till now. And then it'll go and pick a different set of hyperparameter configurations and train the model again on that sub-training set. And again, evaluate it on the holdout set. And it'll do this again and again and again and again. So it's literally, so if it's a decision tree, you're training potentially hundreds of decision trees as you're exploring different hyperparameter configurations. And then once you found the best that you found from your sweep, you then you pick those hyperparameters and then go back to your full training set now, and now retrain your model, and that is now your final trained model for that data partition. Does that make sense?
Yeah, but you do that once. I mean, once you do your K-fold cross-validation, do you need to do that again, over and over again?
Yes, so if you have five-fold, if your original study has five-fold cross-validation, you're gonna train 5 models, and each one is gonna have its own hyperparameter sweep, ideally. What I'm describing you today is what I consider to be, adopting best practices in machine learning. I should just clarify the caveat that there's no one way to do machine learning. Everyone has their own bias, everyone has their own opinion, and I think what I'm explaining to you today is following what I would consider to be best practices, but there is room for interpretation and for variation.